When I do fieldwork, I always take photos, not only because I love capturing memories like anyone else, but because they also serve as an important record of a given moment in history. Like when I went to Madagascar and took hundreds of photos of erosional formations in the rolling hillsides. From those images, we could see how Madagascar's highlands had changed from a once widely forested area to one where deforestation has resulted in serious gashes and erosional gullies called lavaca. With fewer trees, the soil becomes even more vulnerable to these landslide-like events, setting the stage for even more dramatic changes to come. The landscape isn't permanent. It's changed as continents have shifted and humans have interacted with the environment. And it'll continue to change, because our planet is a super dynamic place. Some changes happen slowly. We'd have to watch for millions of years to see the continents drift or the Rocky Mountains grow. But a storm or avalanche changes the landscape in the blink of an eye. Both types of change have tremendous influence over our lives, from small decisions like what we'll wear today, to bigger choices like where we choose to live. All of these changes, above and below Earth's surface, are part of physical geography. And for the first half of the series, physical geography is the lens we'll use to tell the stories of the Earth. I'm Alize Carrere, and this is Crash Course Geography. Up till now, we've been talking about tools and ideas that apply throughout geography. But the Earth is a big and complex place, so traditionally, geography is studied as two interconnected parts: physical geography and human geography. Physical geography is all about recognizing the characteristics of the environment and the processes that create, modify, and destroy those environments. But remember, human-environment interactions are fundamental to studying geography. So as physical geographers, we'll look for answers to our questions in the processes that happen without humans and because of humans. We'll be exploring a particular space, the geoecosphere, which is the narrow zone on Earth's surface that contains all the different landscapes and major systems that interact to create our dynamic planet. By breaking the Earth up into distinct systems, we can look for connections that help us understand complex problems like climate change or the loss of variety of life in different habitats. In physical geography, we think of there being four major Earth systems. First, there's the atmosphere, or the layers of air surrounding Earth that give us clouds, weather, the ozone layer, and the air we breathe. Then there's the hydrosphere, or all of the water on, below, or above the planet's surface. So all the water in the soils, under the ground, in oceans, lakes, ice caps, and streams, as well as in plants, animals, our bodies, and all the water molecules in the atmosphere. Next, we have the lithosphere, which is the rocky outermost layer of Earth. The rocks of the lithosphere form our continents and line the bottom of Earth's oceans. And finally, the parts of Earth where life can exist make up the biosphere. Whether it's a deep, dark, cold spot in the ocean, a barren mountaintop, or a lush, fertile farm field. No matter what we choose to focus on in physical geography, all four spheres will play a role. Like ecosystems are communities of living things interacting in concert with their non-living environment based on these underlying Earth systems. Let's go to the thought bubble. Off the northeastern coast of what we know as Australia is the world's largest coral reef, the Great Barrier Reef. Well, actually, it's almost 3,000 individual reefs that are home to more than 9,000 different species of tiny, fragile yet resilient organisms working together to build their home. Since the Great Barrier Reef, like all coral reefs, is life, the reef itself is part of the biosphere. Even the skeleton of each reef is built by the coral itself. The hard corals of the Great Barrier Reef secrete the chemical compound calcium carbonate, which hardens into limestone. That limestone is part of the lithosphere and forms the rock foundation that protects the corals and other organisms from the waves. Even when the coral dies, the limestone remains and becomes a spot for new coral to grow and thrive. The Great Barrier Reef exists in the Pacific Ocean, underwater, so it's surrounded by the hydrosphere. And the atmosphere still interacts with this marine ecosystem through storms. Believe it or not, these delicate-looking coral reefs are most successful in areas where the hydrosphere and the atmosphere clash, creating lots of waves. It's estimated that thousands of cubic kilometers of ocean waters flow through the Great Barrier Reef each year, bringing food, oxygen, and keeping temperatures moderate for all the organisms that call the reef home. Clashes between the atmosphere and hydrosphere can become destructive, though. All four spheres are involved when high winds and towering waves brought by Pacific cyclones destroy softer corals and damage the more hardy corals. But cyclones bring cooler water into these shallow ecosystems and can clean up the reef by whisking away sediment that is built up over time. Thanks, Thought Bubble. By looking for interactions between all the Earth systems, we can identify what helps ecosystems thrive. We'll talk more next episode about how the Earth formed these spheres and how it moves. For now, though, we can start thinking like physical geographers and ask what causes these four spheres to interact. The Earth's atmosphere, hydrosphere, lithosphere, and biosphere are driven and influenced by the sun and insolation, or incoming solar radiation. For example, the sun's energy heats up liquid water, causing it to evaporate into water vapor. That water vapor may condense in the atmosphere, forming clouds and rain. That rain may enter a river, a lake, or become frozen in a glacier. Over time, that glacier might move down a mountainside, altering Earth's surface and providing a habitat for the smallest of bacteria. As physical geographers, our area of study is everything the light touches, and more. That's a lot of surface area to cover, literally. So just like you can be a doctor but spend most of your time studying the heart to become a cardiologist, physical geographers break up the geo-ecosphere and specialize in different realms and processes. Like, what if we visit Guatemala to look at bananas? No, wait, we already did that. Although that could also be a great geo-ecosphere example. Instead, let's do a similar deep dive into the bananaless Iceland and explore like different types of physical geographers. Let's start with the land itself, which was originally settled by Nordic people around 870 CE. Though it seems to have been known about long before the 9th century by Greek explorers and Irish hermits and monks. And it had other names like Snælund or Gardar's Isle, according to the sagas of Icelanders. It sits on the northern section of the Mid-Atlantic Ridge, an underwater mountain range that runs north to south in the Atlantic Ocean. The topography, or the shape of the land, is a result of processes happening both above and below the surface. From time to time, lava spills out from the fissures in the crust, which means Iceland is still growing. We're starting to picture the geomorphology of Iceland. As geomorphologists, we're interested in the origin and evolution of the shape of Earth's surface, like what role weathering plays in how life survives on Earth, or how the island changes because of the glaciers that have grown and retreated for ages, scraping the surface into the peaks, lakes, and streams that are there today. If we dig in, we'd find most of the soils in Iceland are volcanic soils called andisols. These soils form from volcanic ash and are super rich in nutrients, which in the past allowed forests and grasslands to dominate the landscape. But about 1,000 years ago, settlers cut down many of the forests. Cattle and sheep grazing became possible year-round, leading to overgrazing that ultimately exposed the rich topsoil to erosion. So there's a lot less nutritious soil for plants these days. Pedology is the study of soil types and how they form. And pedologists have helped with the extensive soil conservation efforts that have been in place for more than a century. The rare combination of glaciers and volcanoes not only influences the land, it also influences the water. Hydrology is the study of how water is moved, managed, and distributed above and below Earth's surface, like in rivers and lakes and oceans and groundwater. As hydrologists in Iceland, we'd be very busy keeping track of water distribution and movement. We might want to map the sources of sediment flowing into a river, but we might also ask which parts of a city are most at risk for flooding. As of 2020, about 10% of Iceland is covered in icy glaciers, and yet magma is also close to the surface, providing heat for geysers and hot springs. That heat means there's an increase in the volume of water in rivers due to the ice melting and the increasing runoff. But we'd also study and even help Icelanders manage their water resources to generate hydropower, or power generated from moving water. As of 2015, almost 100% of electricity in Iceland came from renewable sources, like wind and solar, and 73% came from hydropower. The people of Iceland use the physical geography to heat their homes and power their lives. As an island in the North Atlantic Ocean, Iceland's weather and climate are affected by the seas and oceans surrounding it. In Iceland, climatology, or the study of atmosphere and weather patterns over time, is interconnected with oceanography, or the study of the past, present, and future features of the oceans. As climatologists, we might ask how a change of energy in the atmosphere impacts the biosphere and hydrosphere. The North Atlantic drift current brings warm waters northward, which helps moderate Iceland's climate and give it damp, cool summers and relatively mild winters despite being so far north. But not all winters in Iceland are mild. Every so often, the atmospheric energy will change and a storm will batter the island, illustrating how meteorology, or study of atmospheric processes and phenomena, associated with the island can be extreme. For example, a blizzard in December of 2019 dumped up to 3 meters, which is over 9 feet of snow. Even still, the usually temperate climate allows the biosphere to thrive. Iceland is rich in life that makes up biogeography, or the study of distribution of plants and animals in an area. For example, Iceland is home to lots of bird life and marine mammals. Puffins, skuas, and kittiwakes make Icelandic sea cliffs their summer nesting home. Arctic fox, reindeer, and rabbits are also found here, and the occasional polar bear passes by as she travels on icebergs from Greenland. The flora has a harder time. Things like overgrazing, deforestation, the movement of glaciers, and volcanic activity limit growth. Grasses and low-growing shrubs like heather grow, but few large trees exist. So as biogeographers in Iceland, we might investigate how vegetation along sides of streams affects flooding. Or we might get involved in conservation planning and establishing protected areas. Our focus would be on where the biosphere and hydrosphere meet. All these different spheres of Earth could be their own field, and some of them are. For example, ecologists study the biosphere and look at what physically happens as different species interact across the landscape. But a geographer focuses on how ecological processes are distributed across space and how species move and change over time. What differentiates physical geography from other scientific fields is the focus on spatial patterns in the landscapes. Physical geographers investigate not only variation from place to place in the various spheres, but also the complex interaction within and between different spheres and how they change over time and across scales. The Earth has a story that extends back over 4.5 billion years, which we'll talk about more next time. Describing those dynamic twists and turns helps us understand our role here, our future, and the future of the planet. Many maps and borders represent modern geopolitical divisions that have often been decided without the consultation, permission, or recognition of the land's original inhabitants. Many geographical place names also don't reflect the indigenous or aboriginal people's languages. So we at Crash Course want to acknowledge these people's traditional and ongoing relationship with that land and all the physical and human geographical elements of it. We encourage you to learn about the history of the place you call home through resources like nativelands.ca and by engaging with your local indigenous and aboriginal nations through the websites and resources they provide. Thanks for watching this episode of Crash Course Geography, which was made with the help of all these nice people. If you'd like to help keep Crash Course free for everyone forever, you can join our community on Patreon.